Okay, in this exercise, we're going to do second order regression. Before, we've done regression for first order plus dead time constants. In our lesson for this activity, for this class, we regressed the second order plus dead time coefficients. We've regressed PID coefficients. Here what we're going to do is we're going to discuss gain scheduling. So the gain scheduling is where we change the gain of our system depending on current conditions. And so we adaptively estimate the second order model as new data arrives. We could think of this as the system, for example, the dynamics change at high temperature and at low temperature. And so with that, the gain would change. And so this is a way for us to adapt to our systems to use linear gains with a nonlinear process. And so here we have some function, which is our model of our system, which takes our initial temperature, the time, m, which is the magnitude of the step, kp, which is our gain, tau s, and zeta. And so we have an overdamped second order response. I'll go ahead and we'll underline that. Overdamped second order response. And we're going to do a step input of 80%. So we're going to modify this below this temperature to fill in the analytic solution. Luckily, we can do this. We have our response here for an overdamped equation is equal to Kp times the magnitude times this equation right here. So let's go ahead. We're going to have our parameters, which are going to be solved for, which is Kp, tau s, and zeta. Those will go into here. Those are going to be our initial parameters that we're going to use. We also have our initial step change. We're going to connect to our TCLab. We're going to establish our arrays. We're going to start our figure and start hold on. We'll start our timer, and then we're going to start recording measurements. And then after 15 seconds, once we have a little bit of data, we're going to start guessing. And so we're going to do that first by randomizing our guess values. We're going to add some random value. Rand by definition is going to be between 0 and 1. So between multiplying it by subtracting it from 0.5 is going to be either from negative 0.5 to 0.5. And then we're going to multiply that by our tau s and zeta guesses. And that's just so that we don't get stuck in a local minimum and we just had some stochasticity to it. We also multiply these by tau s. Since it's greater, we're going to multiply it by 1, and for zeta by 0.01. Again, the zeta is a much different, smaller scale. So we do that just to change it just a little bit, but we're changing the scale there. And then we change that. Those we use as our weights. So the previous values multiplied by just a little bit of randomness are added to that randomness is added to it, I should say. So we take our previous value and then we multiply it by some value here. That's going to be, we're going to add it, take our previous tau plus either some value between negative 0.5 and 0.5, or this is plus negative 0.005 or 0.005. And we're adding that to it just to, again, just induce a little bit of randomness. We use that as the initial guess, and then we use fmin search to regress what our Kp, tau s, and zeta are every 3 seconds. Then we update our values, and then we continue. So we update the prediction, and we update the heater setting based on that as well, and then we'll graph it continuously. We have a program to graph for us, a function, which will be doing the graphing, and it just has the x coordinates and y coordinates, and it makes it all pretty, and it makes it all have a whole bunch of code in our for loop. We also have the function which will determine our sum squared error. There's a few things going on here. First is that we take the y predicted and the y measured, which we use the model to predict, and we regress that as the difference between the two. We also add a penalty if we violate some bounds. So if tau s is too low or too high in regions that just don't make sense, we're going to add a very large value and also make it differentiable by making it depend on tau s. That's so that our solver knows to get away from those bounds that are just unreasonable. We're using fmin search just because it's going to work a little bit faster. So let's go ahead and print our add our temperature, our analytical temperature equation to all of this, and then we'll go ahead and see how it regresses. I remember it's Kp times m times 1 minus, and now we're going to have to get go back up, look at the equation. Kp times m times 1 minus e to the negative zeta t over ts. We also have cosines here. Actually, this is hyperbolic cosine. And let's go ahead and look at, I had a couple simplifications here within this. So a, b, and c are simplifications. A is going to be exponent of negative zeta times t divided by tau s. B is going to be zeta squared minus 1 and the square root of all that. And then c is going to be t divided by tau s times b. So let's go ahead. Let's see where those appear in our system here. Oop, didn't want to do that. Just trying to get out my pen. Here we go. So if we look right off the bat, I see this is A. Right here, we had zeta square root of zeta squared minus 1. That's going to be B. But t over tau s times b is actually c. So that's c, and this is c, and this is zeta over b. So hopefully that makes things easier. So we're going to have a times hyperbolic cosine of b, or sorry, of c. Let's go to that point. 1 minus a times, we're going to need the actual multiplication there versus just the parentheses, and it was hyperbolic cosine of c. And let's go back up again, look at our equation, plus zeta over b times sine h of c. Not sine h, sine h of c. And then I believe we had 2 parentheses. We'll just scroll over. Yep. Oh, did not want to do that. Control Z. But I like the idea, so let's go ahead and do Control C. And we already started. So we have our initial values, and this is going live. This is with the Temperature Control Lab. You'll notice our temperature is 0 because we're doing the deviation variable here. And we have our temperature, and our Kp values are our tau s value, zeta values. So we can see how these are going to change over time, as well as the current value printed out. So one thing I'm seeing right away is that our measured temperature is going to be different than our regressed temperature or our predicted temperature, because it looks like our predicted temperature is in units of real temperature versus the deviation variable. So we're going to go ahead. I'm going to stop this. I'm going to run down here. I'm going to say lab.off and clear lab so that we don't run into problems when we try to connect again. And then the last thing we want to do is we just want to say T0 plus all of this. It's one of our arguments. So T0 plus all of this, and I'll go ahead and write that there so it's easier to see. T0 plus all of that. Oh, and because I put something in, we're off to the races. This time it's going to start at the temperature, which looks like about 32 degrees. We'll wait till we hit 15 seconds, and it's going to start updating those parameters. That's too bad. I'll see in our graphing equations we have Kp and Kp here. So while that's going, I'm going to go ahead and change our graph. This right here is our Kp ray. This should be a tau s. And this should be a zeta. So let's just keep in mind those aren't what they think they are. So we can see our zeta is obviously, it's very overdamped. Our zeta is very high, same with our tau s, and our kp is staying at 1. That's interesting. So to me, that tells me that we're playing with those two and that our solver isn't doing a good enough job at updating those values. If we come down here, let's maybe just look at our solver arguments up here in our loop. Kp, tau s, and zeta. We'll see, maybe it's just a function of it being a high temperature, and so things are out of whack. These are at the top of their bounds, which again isn't a good sign. So what probably needs to happen is if we just need to get these to a better value to start, that would be ideal. As far as a better initial guess would probably help us. So let's look at our initial guesses within this system. Our initial guess for Kp is 1. Our initial guess for tau s is 50, and zeta is 1.2. And so from 1.2 we get all the way up to 5. Maybe what we really need is just a little bit more of a random number coming in and messing things up. So tau s, what are the bounds on tau s? It's from -10 to 200, and we're just changing it by 1. Let's go ahead and change that by 10. And same thing with r. Zeta could be between 1 and 5. So let's go ahead and add 1 to, or at least 0.5 to it, which is what r would do. R by itself. So this is going to add 5. Really we could add 100 and make it 50 for this one. That'd be a little bit weird though. So I like 10 there. We'll just do 0.5 there with this zeta. Unless we're only graphing, I only see our measured temperature on here too. So let's go down to our graph one more time. Our arguments are I, the time array, temperature array. So we should have two things being graphed here, but there's no hold on. Classic. Stop it. Again, we're going to go lab.off and then clear lab. Let's go ahead and run it, just make sure everything's running right, make sure we have our temperatures run right. We have tau s, zeta. These are still our initial conditions, but now we at least see that. Obviously, I don't love this. It's going to cause some problems, because it's going to go all the way down. And they're both being marked as measured temperature. So you can see this is an iterative process. Hopefully it makes you feel better about the times you graph and it doesn't go like you planned. We have our temperature is already at 60 because of what we previously did, and so it's going to use that 60 and it's going to project that it's going to go upward due to our second order plus dead time, where really it's just going to stay constant. And so that's where we're going to have these weird constants. I'll go ahead and pause it. We'll let it cool down and go from the beginning. Alright folks, here we have our solution. You'll notice we follow the temperature very well all the way through this. And as we do so, we see our gain changes, as well as our time constant and our zeta. The point here is that as temperature changes, our system will behave differently. And so we can adapt to that. And that will actually be a subject we discuss later on, just as a survey of moving horizon estimation, where we take recent performance and only use that recent performance to estimate how our system will perform. I'll show you really quick where our error was within our estimation. You see here, this is our objective functions, and then where was it? Right here. So when we do our fmin search, we give it our objective function, like we've talked about, our parameters, the time array, and the temperature array. And instead of giving the array, we only had one value within here. And so that's where the mistake was coming from. But there we go, and you can see that's a very awesome fit. I really like that. So we ended up having some success here. All right, thanks for watching along.